Hello students, in this video lecture I am going to discuss the second part of the solution of the problem of vibrating string using the method of separation of variables. We have already discussed the first part in my previous video, and now in continuation with that we are going to take the solution little further, but let me just recall what we had done in that first part when we were solving the problem of vibrating string using the method of separation of variables. So what we had in hand was this partial differential equation utt is equal to c square uxx subjected to the conditions ux0 is equal to fx, utx0 is equal to gx, u0t is equal to 0 and ult is equal to 0. So this was the problem that we were dealing with in my previous video, the first part of this solution, and this is the partial differential equation of second order that we were solving. Utt is equal to c square uxx, which is wave equation, and this represents the problem of vibrating string. Now we have to solve this wave equation or this second order partial differential equation subject to these four conditions, out of which the first two conditions are conditions in which we have taken t to be equal to 0. T here is greater than equal to 0 actually, and t represents the time, and x, which represents the horizontal distance, this x lies between 0 and L. This has already been discussed in the first part. Here in this particular case, in these two conditions, t has been taken as 0. So basically these are initial conditions where we are taking the time t to be equal to 0, and in these two conditions are conditions on x. Here x has been taken as 0, here x has been taken as L. So these two, the first two conditions are the initial conditions, the next two conditions are the boundary conditions. So subject to these two initial conditions and these two boundary conditions, we were interested in finding out a non-trivial or a non-zero solution u of this problem. And what we had done in the method of separation of variables was that we had assumed our solution to be u is equal to xt, where capital X is a function of small x and capital T is a function of small t, and we were looking for a non-trivial solution of this type. Now what we had done was that we had substituted u is equal to xt in this problem, and we had reduced this partial differential equation. When you actually make the substitution u is equal to xt in this partial differential equation of second order, subsequently we had seen that this partial differential equation of second order gets transformed into two ordinary differential equations of second order. One was this ordinary differential equation in terms of capital T, which was t double dash, I have already written it on the board, t double dash minus lambda c square t is equal to 0. This was the first differential equation that we got in terms of capital T, and then the second differential equation which was x double dash minus lambda x is equal to 0. This was the second differential equation, ordinary differential equation that we had. And again also when the substitution u is equal to xt is made on these two boundary conditions, which are conditions on x here, then we had seen that corresponding to these two conditions, these two boundary conditions, the two conditions that we obtained were x0 is equal to 0 and xl is equal to 0. So this was the first system that had been obtained in the previous video. I had explained this in detail, and this system we had solved for a non-zero value of capital X, because actually we are looking for a non-zero value of u, and u has been assumed to be product of x and t. So if you want u to be non-zero, then x and t both should be non-zero, which means that we are looking for non-trivial or non-zero values of capital X, and we are looking for non-zero values of capital T. So this system we had already solved, and we had found out that this system has a non-trivial solution capital X for some particular values of lambda, and some particular value of lambda, and it was seen that there was not just one value of lambda that we got. In fact, there were infinite values of lambdas given by lambda n, where lambda n were all less than 0, and for these particular values of lambda n, which were actually given by this, I have written it already on the board, that minus lambda n is equal to n pi by L whole square. For these values of lambda n which are all less than 0, here we can always find non-trivial values of capital X which satisfy this system. That we have already seen, and in fact those non-trivial values corresponding to lambda n are given by these. These were the non-trivial values of capital X. So this we have already solved. This system has already been solved. The non-trivial solution for this system, or the non-zero value of capital X, has already been obtained in the previous video. Now what I am going to do in this second part of that solution is that I am interested in solving this particular second order ordinary differential equation, and I want to find out a non-trivial solution T of this system, or of this differential equation corresponding to these values of lambda n, because these are the only values for which capital X is non-zero. So for these particular values of lambdas, or these lambda n's, I am going to find out what is the solution that what is the non-trivial solution that we have for capital T for this particular ordinary differential equation. So these are the values of lambdas that we are going to take, and we are going to solve this ordinary differential equation of second order, and I am going to find out the values of T, capital T, which satisfy this differential equation. Also, after having done that, we will take these two initial conditions also into consideration, which we have not taken so far. So this is the crux of the whole second part, which we are going to do in this particular video. So let me start with the second part of the solution. So we determine Tt from the ordinary differential equation of second order, T double dash minus lambda c square T is equal to 0. This was marked as 9 earlier in the first part, and we have already seen that xx, this is the general solution xx of this differential equation, x double dash minus lambda x is equal to 0, which we had marked as 8. The general solution is given by this. This we have already done in the first part, and this we had labeled as 21. Here a and b are arbitrary constants, and here we have this solution 21 actually represents the general solution of the differential equation 8 without using the conditions x0 is equal to 0 and xl is equal to 0. These are two boundary conditions. So without using these two boundary conditions, the modified boundary conditions that we have got, so without using these conditions, the new boundary conditions that we have got, the solution before using these new conditions comes out to be of this form, which we had marked as 21. Now I am interested in finding out, or I am interested in rather solving this particular differential equation which is in capital T, and it is a second order ordinary differential equation. Now if you have a look at this equation 9, which has been again written over here, so this equation actually resembles 9 is similar to 8. The only difference between the two equations is that instead of capital X, here we have written capital T, and instead of lambda we have written lambda c square. Otherwise the form of equation 9 is just similar to the form of equation 8, which means that because the form of 8 and 9 are similar, this means that the solution, you can use solution 21 for writing the solution of equation differential equation 9. And if you consider this particular form, then the solution of this form, this particular differential equation therefore can be written as, instead of xx I will write tt. Tt is equal to, instead of a you can take constant b, a and b have been taken, so I can take constant, arbitrary constant to be c, and then cos instead of under root of minus lambda, because instead of lambda it is lambda c square, so here I will write minus lambda c square. Then instead of small x it should be t, small t, because capital T is a function of small t, plus the second term is going to be d, the arbitrary constant d. Instead of b I am writing d, and then sine under root of minus lambda instead of lambda, because here lambda was there, so lambda was there, here lambda c square is there, so here I will write lambda c square t. This is what I have. And now if you write this particular solution over here, now again here, because it is before even I write this solution in this form, we have about this point I have already discussed that we have to take the values of lambdas to be given by this, because we have already seen that this particular ordinary differential equation has a non-trivial solution only for these particular values of lambdas that we have seen. So we have to take lambda, so there is not one lambda for which we will have a non-trivial solution. There are infinite number of values of lambda, and these lambdas which we are denoting by lambda n's, are all less than 0, and this is how their value is given. So this has been done in the first part of the solution. So these are the values of lambda n's that we take over here, and again c square under root c square means that c comes out of the root, so that has been done. Instead of lambda I am writing lambda n under root of minus lambda n under root of minus lambda n, and now corresponding to each value of n there will be arbitrary constants. So instead of writing c and d I am writing cn and dn, and corresponding to each value of n there will be a corresponding value of capital T. So this means that there is not one value of capital T that you obtain which is a non-trivial solution of this system, but there are many values that you obtain for each n varying from 1, 2, 3 and so on. We have non-trivial solutions or non-trivial values of capital T. So this is how the solution, the general solution of capital T, the non-trivial solution of capital T for this particular ordinary differential equation of second order is given, and it is given by T and T is equal to Cn cos under root of minus lambda n C into T plus Dn sine under root of minus lambda n C sine of this into T. This we have marked as 27, and now here Cn and Dn are arbitrary constants. Now again we can put the value of minus under root of minus lambda n at both the places. So this is the value which is given, the value of under root of minus lambda n. If we bring this square over here, so value of under root of minus lambda n is n pi by l. So this is the value that I substitute over here, n pi by l, n pi by l. So this is the value of T and T, or this is the solution. These are the non-trivial solutions for this particular ordinary differential equation where n varies from 1, 2, 3 and so on. So this we have marked as 28. All these numbers are coming in continuation with the solution that we have done in the part 1. So this 21 equation was already there when we discussed the first part. So this equation was marked as 25 in the last video that discusses the first part of the solution, and then again this one, this 27 has been given in continuation with 26. So this is the last solution that we have found, that we had found out in the first part of the solution, the non-trivial values of capital X for this particular differential equation. These are the solutions that we had calculated in the first part of the solution, and we had marked these equations as 26. Here n varies from 1, 2, 3 and so on. So all these are non-trivial values of capital X which satisfy this differential equation. So this equation number was coming in the first part of the solution. In continuation with that, this has been marked as 27, and this particular value gives the non-trivial solutions of this differential equation. And then after putting the value of under root of minus lambda n at both the places as n pi by l, this is the final solution that we have, final non-trivial solution given by 28 that we have for this ordinary differential equation. Now again we had assumed in the beginning that u is given by x into t, capital X into capital T, where capital X is a function of small x and capital T is a function of small t, and that this had been marked as 6. Now we have seen that there is not one value of one non-trivial solution or one value of x that we obtain, but we obtain so many non-trivial solutions. Also we have seen that there is not one value of t that you obtain for as a solution of this differential equation, but there are infinite values that you obtain for n is equal to 1, 2, 3 and so on. So this means that there is not one solution that you will obtain for which satisfies the initial value problem, initial boundary value problem that we had taken in the beginning, but for every value of n that you take over here, for every xn and for every tn, you will have u and xt will be a solution of the given initial boundary value problem that we took in the beginning. So this is how the solutions would be given, and now you just have to make the substitution. So u and xt would be given by Bn sine n pi x by l. This is the value of x and x that we have substituted, and again we will substitute the value of t and t. The value of t and t is given by Cn cos n pi c by l t and plus Dn sine n pi c by l t. So this is the value of t and t, and now just taking Bn into Cn together, multiplying Bn with Cn and calling Bn Cn as an arbitrary constant Tn, and then multiplying Bn with Dn and calling Bn dn over here as another arbitrary constant Bn. So this term I have written first, this square bracket I have written first, and the sign term I have written in the end. So this I have marked as 29. So these are the solutions, these are the non-trivial solutions UNXT of the original initial boundary value problem that we took in the very beginning in the first part of the solution. So this is the solution that we have obtained so far. UNXT is equal to an cos n pi c by lt plus bn sin n pi c by lt. This expression multiplied with sin n pi x by l, and this was marked as 29, where we had seen that the arbitrary constant small an, this is the product of the arbitrary constant capital Bn and the arbitrary constant capital Cn, and the arbitrary constant small bn is the product of the arbitrary constant capital Bn and the arbitrary constant capital Dn. So this we have already seen. Now also we can see that this is not one solution that we have obtained for this one dimensional wave equation, which is a partial differential equation of second order, which we were trying to solve and which represents the problem of vibrating string. So this is not one solution that we have obtained for this partial differential equation, rather we have obtained infinite number of solutions, because n varies from 1, 2, 3 and so on. And so these are the solutions that we have obtained for this partial differential equation. Also one thing which we can note from here itself is that this is a linear homogeneous partial differential equation. So if all these are solutions of this equation, because it is linear and homogeneous, so sum of the solutions will also be a solution of this equation, which means that this series which we are representing by uxt, this series which is sigma n varying from 1 to infinity, and the sum of solutions of this type, summation n varying from 1 to infinity, this expression is same as this an cos n pi c by lt plus bn sin n pi c by lt multiplied with sin n pi x by l. This whole thing, this series will also be a solution of this partial differential equation of second order, provided this series is of course convergent. So supposing that these conditions are satisfied, so this solution that we get is a series solution of the one dimensional wave equation, and this we are representing by uxt, and the number that we have given to this is 30. So 30 we have obtained as a solution of this one dimensional wave equation in a series form. Now the only thing that now remains to be used are the initial conditions which were present in the original initial boundary value problem, which we have not used so far. So these are the initial conditions that were present in the initial boundary value problem. Ux0 is equal to fx and utx0 is equal to gx, where x lies between 0 and l, and these conditions we had marked as 2 and 3. So now you have to make use of these two initial conditions, and you have to modify the solution which you have obtained in the form of series so far, which is given by 30. So now making use of this initial condition in 2 over here in solution 30, for making use of 2 in 30, here f and g, of course I have explained this already, f and g are prescribed functions. So for making use of 2 in 30, you just have to put t is equal to 0 everywhere in the left hand side and right hand side on 30. So when you put t is equal to 0, you will get ux0, and ux0 is nothing but fx, so you will have fx over here. Instead of ux0, I will write fx, and then again when you put t is equal to 0 at both the places, here this will become sine 0, and sine 0 is 0, so this term vanishes. Here this will be cos 0, because when you put t as 0, this will be cos 0, cos 0 is 1, so here you will be left with only an. So basically inside the summation, or inside the sigma sine n varying from 1 to infinity, you will be left with just an sine n pi x by l, which is what I have written over here. So this is the expression that you get for fx in the form of series, that is fx is equal to summation n varying from 1 to infinity an sine n pi x by l, and this we have marked as 31. So this is the one expression or one condition that we have obtained by making use of one initial condition. Now making use of another initial condition that was given in the initial boundary value problem, which is utx0 is equal to gx. Now in this initial condition ut is present, which is the partial derivative of u with respect to t. So for making use of this condition, you need to have ut first, and what we have is u. So this means that I will differentiate this expression 30, this expression in 30 with respect to t partially. So this is what I am going to do, differentiating series, the differentiating series 30 with respect to t partially. We get here you will have utxt summation n varying from 1 to infinity. This is as it is. When you differentiate the first term with respect to t partially, an, the derivative of cos theta is minus sin theta, so you will have minus sin n pi c by l t into the derivative of this expression using chain rule, which is the derivative of this expression is n pi c by l. So that n pi c by l, which we have taken it outside because this n pi c by l will come in the derivative of the second term also. So we have taken that common. Now coming to the second term, the derivative of sin theta is cos theta. So it is cos, the derivative of sin n pi c by l t is cos n pi c by l t. Bn is as it is, and then into derivative of this particular expression by chain rule. And as far as this particular term is concerned, sin n pi x by l is, it doesn't have a small t, so this will remain as it is when we are calculating the derivative. So this is the expression that you have for utxt, the partial derivative of u with respect to t, which we have marked as 32. Now we can make use of the initial condition utx0 is equal to gx, which is 3 in 32, and you just have to put t is equal to 0. When you put t is equal to 0, utx0 is equal to gx. So this is what we have. And when you put t is equal to 0 on the right hand side, this expression will become sin 0, and sin 0 is 0, so this will vanish. This expression will be cos 0, cos 0 is 1, so bn will be retained. So you will have bn as it is, n pi c by l is as it is, and sin n pi x by l, this is as it is, and this is the expression that you have for gx. So there are two series, and we have marked this as 33. So there are two series that we have obtained. One is one series gives you the expression for fx, the other series gives you the expression for gx, where f and g are prescribed functions. They will be already given to you in the question. So these are two series, we can see these two series are series containing sine terms, and these series fx and gx can be represented by the Fourier series. These are of the form of Fourier series. So fx and gx can be represented by Fourier sine series, provided these coefficients are given are Fourier coefficients which have a particular value. About Fourier sine series I have already discussed when we were discussing the heat conduction problem. So this is the precisely this is the Fourier sine series that was coming in the heat conduction problem in my earlier video, and we had seen that if this is to represent Fourier sine series, then these coefficients an should be given by this. An is equal to 2 by l 0 to l, this is 0 to l fx sin n pi x by l. This is what we had. So this part we have already discussed when we were discussing the heat conduction problem. This is n pi x by l. So if fx is to be represented by a Fourier sine series like this, then you have the coefficients an must be of this form, the Fourier coefficients. These are the Fourier coefficients and they must be of this form. So ans are given by this. Now likewise, if gx is to be represented by a Fourier sine series, then these coefficients must have a value. They must be represented, these coefficients must be represented by Fourier coefficients. And how are these Fourier coefficients given? Now here the only difference is, here instead of an, the difference between fx and gx is this expression and this expression is that instead of fx you have gx is written, and instead of an you have bn sin n pi c by l is written. So here to obtain the values of bn's, we can just replace an by this expression, because this expression is playing the role of an. So this is what actually you have. Instead of an I write bn n pi c by l, this is the left hand side, and this is equal to 2 by l, this is as it is, 2 by l integral 0 to l, this is as it is, this is 0 to l, and instead of fx you have gx, so I write gx, and this is sin n pi x by l, sin n pi x by l. dx. So this is how we write the values of the coefficients for this particular series if it has to be a Fourier sine series. And now L and L gets cancelled out, and this n pi c by n pi c comes down, and so the values of bn's comes out to be n pi c, which means that this is how the arbitrary constants bn, this is the value the arbitrary constants should have if this has to be a Fourier sine series. Now, so this is what I have written: bn is equal to 2 by n pi c integral 0 to L, this limit is from 0 to L, this is 0 to L gx sine n pi x by L dx. So this we have marked as 34 and 35. So we have reached the end of the problem that we were trying to solve, the initial boundary value problem that we were trying to solve, which was the problem involving the wave equation utt is equal to c square uxx subjected to two initial conditions and two boundary conditions. We have already found out a series solution of this particular problem subject to two initial and two boundary conditions. This is the series solution. So solution is given by solution of the given problem, the given initial boundary value problem is 30, is given by 30, which is a series solution where how are the arbitrary constants given, where an's and bn's, which are the arbitrary constants, are given by these two equations 34 and 35. So this solution, which is in the form of a series solution, has been obtained using the method of separation of variables. So that was all about the solution of the problem of vibrating string using the method of separation of variables.